Hello everyone, welcome to Math World. This video is to discuss Cambridge International AS and A-Level Mathematics Paper 6, which is the Probability and Statistics 2 for May-June 2021, and the code is 9709/63. So let's get started. Question number 1. The number of goals scored by a team in a match is independent of other matches and is denoted by the random variable x, which has a Poisson distribution with mean 1.36. So this 1.36 is for one match because it's in a match. Now a supporter offers to make a donation for $5 to the team for each goal that they score in the next 10 matches. Right. Now find the expectation and standard deviation of the amount that the supporter will pay. So a match, it will be mean of 1.36 goal. Okay, that means now in 10 matches, so I will write lambda equals to 1.36 times 10. That is going to be 13.6. So it's expected to have 13.6 goals in 10 matches. Now, expected is E, right? So from here, I know that my Poisson, my Y is basically, okay, because the X is in a match, right? So I will say that my Y is 10X because X is a match. So therefore, my Y is Poisson distributed with mean 13.6. Okay, and now you need to calculate the expected of the amount that the supporter will pay. So $5 for each goal. That means now here E5Y. Okay, so that means this is going to be 5 EY because of $5 per goal in 10 matches. So therefore, the mean for your information, Poisson, the mean, this is mean, and also variance for Poisson. Okay, so it will be 5 times 13.6. Then this is going to be 68. So that will be $68. Right? Okay, so for the standard deviation, before I get the standard deviation, I will calculate the variance first. So variance of 5y, that will be 5 squared variance y. Then you will be getting 25. Variance is same as 13.6. So 13.6, that means this is going to be 340. Then this is dollar sign. Alright, so that means now here I'm getting the standard deviation. So standard deviation, it will be square root of $340. So standard deviation of 5y, that is going to be square root of $340. Then end up with 18.4, which is equal to 3 significant figures. So that is the solution for question number 1. For question number 2, in the past, the time in hours for a particular train journey has had mean 1.40 and standard deviation 0.12. Now, following the introduction of some new signals, it is required to test whether the mean journey time has decreased. Okay, the mean initially 1.40. Now you want to check whether it has decreased. So now state what is meant by type 2 error in this context. So for information, probability of type 2 error is defined as probability of except H0, given that H0 is false. Okay, so now from here I know that my H0 is basically mu equals to 1.40. So probably I write here H0 mu equals to 1.40, and then now you want to test whether it has decreased. So your H1, that means your mu is less than 1.40 because decrease. So when type 2 error means that accept H0. So we accept H0, which means 1.40 is a mu, but given that the H naught is wrong, okay, it's false. So my interpretation in this question is type 2 error means the mean journey time has not decreased. Okay, because we accept H naught. So mu remains at 1.40. So has not decreased. That is to accept the H naught, when in fact it has. Because based on the definition, given that H naught is false. Alright, so basically it has decreased, but we will just say that it has not decreased. We have to accept mu equals to 1.40. So that's all for the 2A. Now B, the mean time of the for the random sample of 50 journeys is found to be 1.36. This is the X bar. Now assuming that the standard deviation of the journey times is still 0.12 hours, right? Test at 2.5% significant level whether the population mean journey time has decreased. Okay, so this is a standard deviation. Now, I will say H naught, the mu remains at 1.40. H1, we suspect it has decreased, so mu less than 1.40. And now here, 2.5%. So alpha equals to 0.025. And now when we look at the question never mentioned normal distribution, but because the n is large, 50, therefore we will approximate to normal distribution based on the central limit theorem. Therefore now here I will sketch the normal graph, which is a bell-shaped curve. Okay, symmetrical at 0, and then since it is less than 1.40 at the H1, that means it's lower tilde. And then the region here is 0.025 due to the alpha value. Then now here, when you look at the normal graph, our region is always from the positive side. Okay, I mean the critical line should be on the positive side. Therefore, when I reflect it in the line the z equals to 0, it will be 0.025 on the right side over here. But then the region given in the normal table is always towards the left hand side. That means now this total region is 1 minus 0.025, that is 0.975. Okay, and now you have to read the table. This value, when the probability is 0.975, the value is basically 1.96, right? But then our actual value is on the left side. Therefore, I will label negative 1.96. Okay, so here I write 1.96, but it's a negative value. Okay, because the total regions here is 0.975. Alright, so based on this graph, I can write down my rejection criteria, that is reject H naught if the calculated value of Z or Z is less than negative 1.96. Okay, so now here we need to do the calculation, so I'll do it side by side. My calculation is Z or Z equals to my X bar minus mu over standard deviation is given. Okay, so 0.12, I will write sigma over, this was supposed to be 50 journeys, standard deviation, assuming still okay. So let's see. The standard deviation actually given, this is a standard deviation, population standard deviation, that means it's sigma. So I will write sigma over square root n. Okay, then for the calculation wise, the X bar is 1.36. minus the mu is the mu at the H naught, that means 1.40, over standard deviation is given 0.12, then divided by the n is 50 here. Okay, then here you will be getting the value of negative 2.36. Now mark this value on the graph. Negative 2.36 is basically inside the region. Okay, therefore from here I will just write, since the calculated value is less than negative 1.96. Therefore, we reject H naught based on the rejection criteria. So this is a decision. So when reject H naught means that we have sufficient evidence to say, to conclude the time has decreased, right? So there is sufficient evidence to conclude at alpha equals to 0.025, because this decision is only valid for alpha equals to 2.5%. That's the population mean journey time has decreased. Alright, so this is the solution for part B. C states with a reason which of the types, type 1 or type 2, might have been made in the test in part B. Okay, so go back to part B. Part B, our decision is reject H naught. Alright, so for your information, type 1 error is defined as probability of reject H naught given H naught is true. Okay, whereby the type 2 error is defined as we accept H naught. That means now from part B, since our decision is reject H naught, right? We have rejected the H naught, therefore it will be type 1 error. Okay, so here, right, type 1 error have been made. Because now you need to give a reason as, or you just write as, H naught was rejected. In part B. Right, so done for part C here. Question number 3. The local council claims that the average number, that means this is the mu, of accidents per year of a particular road is 0.8. Now Jane claims that the true mean, which is a mu, this is a mu, is greater than 0.8. She looks at the records for a random sample of 3 recent years and finds that the total number of accidents during those 3 years was 5. Okay, this 0.8 is for 1 year, right? 0.8 accidents. Now, A, assuming that the number of accidents per year follows a Poisson distribution. First part, state now an alternative hypothesis for a test of Jane's claim. Now look at Jane's claim. Jane claims that for 3 recent years, it was 5 accidents. That means now here our H naught cannot base on 0.8, right? So you have to convert to 3 years. So 0.8 per year, 3 years will be 0.8 times 3. That is 2.4. Therefore, my H naught, which is a null hypothesis, I will write mu or lambda, okay? Since this is Poisson distributed, so I will write lambda equals to 2.4. And then Jane claims that it is greater than 0.8 per year. So therefore, expected mu is greater than 2.4 because now here we are considering 3 years. So done for first part. Now, second part, test at 5% significant level whether Jane's claim is justified. Okay, so now here I will write H0, H1 done already. So probably I will just write alpha is 0.05. Okay, then just write reject H naught if probability of X. Now look at here, the H1, because this is greater than, right? Therefore, it's upper tail. Here, it will be greater equals to. Now, it's mentioned that it was 5. Therefore, greater equals to 5 is less than 0.05. That is the critical, this is the rejection criteria. But if let's say your H1 is mu, your H1 is lambda less than 2.4, then here it will be Px less equals to 5. And then less than 0.05. So that is how we decide whether this symbol here is greater than or greater and equals to or less than equals to. It all depends on your H1. Okay. So now here I need to calculate. So because we know that now your X is basically Poisson distributed with mean 2.4. Okay, 2.4. And now for P, probability of X at least 5. So for Poisson distribution, this is the formula. Px equals to X. This is going to be E minus lambda times lambda power X over X factorial. Then the X starting from 0 until infinity. Okay, so at least 5 means it will be 5 onwards until infinity. So we have difficulty in calculating that probability. Therefore, I will use total probabilities 1 minus all previous probabilities. And remember, our X start from 0. That means this is X less than 4. Okay, less than equals to 4, which means it will be from 0 until 4. So you minus all previous probabilities. Okay, then here it will be 1 minus. Now, when you look at the formula here, actually this E minus lambda is a fixed number. So I will write E minus 2.4. Okay, because your lambda is 2.4. When X goes to 0, any value to the power of 0, it will be 1. Then 0 factorial in the denominator also 1. Therefore, I will just write 1, then plus 2.4 degree 1 over 1 factorial. Just leave it as 2.4. Then 2.4 degree 2. Because I have factorized the exponential. From exponential negative 2.4. Then when X goes to 3, it will be 2.4 degree 3 over 3 factorial. And then lastly, 2.4 degree 4 over 4 factorial. Then when you calculate this, it will be 1 minus 0.90413. That will be the total value of the values inside the brackets. Okay, then you will be getting 0.0959. Now you compare with this. So you need to compare with 0.05. This is greater than 0.05. Okay, so now I will just write since the probability is greater than 0.05, so according to this criteria, this rejection criteria, when it is less than 0.05, we reject H naught. Therefore, now, since here no longer less, therefore we do not reject H naught, or I would just say we accept H naught. So when accept H naught, go back to the H naught. That means you have not sufficient evidence to conclude the H1. Okay, so I will say insufficient evidence to conclude the mu or true average is greater than the value. Or you want to check whether Jane's claim is justified. So since we accept the H naught, therefore there is insufficient evidence to conclude Jane's claim is justified, because we cannot accept her claim. Okay, so done for this calculation. Now B, Jane finds that the number of accidents per year has been gradually increasing over recent years. State how this might affect the validity of the test carried out in parts A 2. Okay, parts A 2 means the hypothesis testing, right? So from here, because it has been increasing gradually, that means now here means that the mean is not constant, right? Therefore, the Poisson distribution is not valid. Excuse me. You can say Poisson distribution or Poisson model is not valid. Okay, so this is the effect of the validity of the test. Now, just for information, for Poisson, okay, Poisson distribution, it has few conditions to be fulfilled. The first one is events are independent. So here still independent. Second, the average rate, that means the lambda, is constant. Okay, then the third is two events cannot happen at the same time. Okay, so these are the three conditions for Poisson distributions. For Poisson distribution. Okay, now for question number 4. The measures m kilograms of flour in a random sample of 90 sacks of flour are summarized as follows. So n is 90, summation m 4500 is 9, summation m squared equals to this much. Now A, find unbiased estimates of the population mean and variance. So unbiased estimates for mean is basically the m bar. Okay, so m bar, that is summation m over n. Then just replace the values and you will get 50.1. Then the unbiased estimates for variance, that is the SM squared. So this is the sample variance. Formula is 1 over n minus 1 summation m squared minus square of summation m over n. Then this is going to be 1 over 89. Summation m squared is 22, which is given here, 225,950. Then minus square of summation x, square of summation m, 4509 squared over 90. Then this value is going to be 0.552. Correct to 3 significant figures. Now calculate 98% confidence interval for the population mean. So now here 98% confidence interval for mu, right? For mu, then this is going to be m bar plus minus z. Now 98% means the middle is 98%. That is 0.98. So we have another 0.02 for the left and right side. So left each side it will be 0.01. Okay, 1 minus 0.98, that is 0.002, that is shared by two parts, therefore 0.01. So here I will write 0.01. Then after that, SM squared over n square root. Okay, so now the M bar already calculated just now. So you found 50.1. So this is going to be 50.1 plus minus. Okay, now here, look at the question. The N is 90, even though it does not mention normal distribution, but since N is greater than 50, according to the central limits theorem, it will be approximate to normal distribution. Therefore, again, this graph will be a normal graph, or I'm using z-test, okay? Normal test, that's why here Z. So then you refer to the normal table. And total here, because for normal table we are interested to know the total region. So for information, this is 0.01. So when you add up these two regions, that is 0.99. Okay, so when 0.99 means that the value is going to be 2.326. So the other one is negative 2.326 and the middle is 0. So from here I will just write 2.326, then square root of SM squared. That is the variance that we have found just now, 0.552. So here I will write 0.552 over the N here is 90. Okay, so when we calculate using the minus over here and round up to 3 significant figures, you will get 49.9. That is our lower limit. And now calculate using the plus, that it will be 50.3. So this will be our confidence interval. Now see, explain why it was necessary to use central limit theorem in answering part B. Okay, because the population of masses is not normal. Because never mention normal. It's not normally distributed. Okay, D, find the probability that the confidence interval found in B is wholly above the true value of the population mean. Okay, probability, that's the confidence interval is above. Now look at here. The confidence interval is 0.98. So when it is above that confidence interval, obviously this is 0.01. Okay, so the calculation here, it will be probability equals to 1 minus 0.98, then divided by 2. That means you are getting 0.02 divided by 2, hence 0.01. So that is the solution of D. Number 5, most plants of a certain type have 3 leaves. However, it is known that on average, 1 in 10,000 of these plants have 4 leaves. And plants with 4 leaves are called lucky. Now, the number of lucky plants in a random sample of 25,000 plants is denoted by X. So A, state with a justification and approximating distribution for X, giving the values of any parameters. Okay, so basically at first your N is 25,000. Okay, this is 25,000 plants. And then the probability, right? Probability to get 4 leaves. That is 1 in 10,000. That means the probability is 1 over 10,000. Right? So now we need to calculate. Now look at here. At first your N is 25,000, which is greater than 50. Okay, because state with justification. And then now I need to calculate what is my NP. So 25,000 times 1 over 10,000. So you will get 25 over 10. That is 2.5. And this is less than 5. So when N is greater than 50, NP is less than 5, right? Instead of binomial, this one supposedly binomial, then now becomes Poisson. Okay, so from here I would say X is Poisson distributed with 2.5. So this is my approximating distribution for x. Now use your approximating distribution to answer parts B and C. B, find px less equals to 3. Okay, so now your x is Poisson distributed. The mean is 2.5. Now for your information, initially it was binomial. So binomial is discrete, random variable, and then the Poisson is also discrete. Therefore, here we do not need to consider the continuity correction factor, right? So just direct calculate using Poisson formula. So x less equals to 3, it will be px equals to 0 until 3. And the formula just now was x is Poisson lambda. The probability of x, it will be e minus lambda, lambda power x over x factorial. So the x starting from 0 until infinity. So which means this is e minus 2.5, then 1 plus 2.5 plus 2.5 degree 2 over 2 factorial plus 2.5 cube over 3 factorial. Okay, then here you will be getting 0.758. So that's the part B solution. C, given that px equals to k is same as double of px equals to k plus 1. Find k. Okay, so now here just use the formula px equals to k equals to 2 probability of x equals to k plus 1. So that means now here it will be e negative 2.5, 2.5 to the power of k over k factorial equals to double of e negative 2.5, then 2.5 to the power of k plus 1 over k plus 1 factorial. Okay, so obviously the exponential can be cancelled off from both sides. Okay, then now I use cross multiplication, just multiply. Then you will be getting, okay, I will keep the factorial on one side. Okay, then the 2.5 I will move down. That will be better. So it means that I will keep the, okay, wait, I don't want to use cross multiplication. I will keep the k one side, right? K one side, and then this one I will move down. So which means now here I will get k plus 1 factorial over k factorial equals to 2.5. There's a 2 outside. The power of k plus 1 over 2.5 to the power of k. Okay, so now here 2k plus 1 factorial over k factorial, just for information. If let's say 2 factorial, that is 2 times 1. If 3 factorial, that is 3 times 2 times 1. Okay, so from here I will say that this 2 times 1 I can change to 2 factorial, which is here. So I will say 3 times 2 factorial, which means I'm getting this result. But if let's say I replace my 2 by k, that means my 3, it will be k plus 1. This is k plus 1 because 3 is 2 plus 1. Therefore, from here, I'm getting an important result, right? So 3 is replaced by k plus 1, then k plus 1 factorial equals to the 3 is k plus 1, and then the 2 factorial is basically k factorial because my k is 2, so k factorial. So I'm getting this important result. This is for me to simplify the left-hand side. So therefore, I will write, okay, this k plus 1 factorial is basically k plus 1 times k factorial. Then over k factorial. And then there is a 2 there. Now, you have the same base and division. So from pure mathematics, right? So you will have a degree m over a degree n. That is a degree m minus n. Right? Therefore, now here I will write 2.5 degree k plus 1, then minus k because of division. Right, so from here, the k factorial will be cancelled off from the left side. Then now I will be getting k plus 1 that equals to 2 times 2.5. So the power, when you simplify, that is degree 1. Okay, so 2 times 2.5 is basically 5. So I will get k plus 1 equals to 5. Hence, my k is basically 4. So this is the solution of part C. Now the number of lucky plants in a random sample of n plants, where n is large, is denoted by y. D, given that probability of y at least 1 is 0.963, correct to 3 significant figures, use a suitable approximating distribution to find the value of n. So now your y is Poisson lambda, okay, because now we do not know what is the, it depends on your n, but since your p is very small, look at here, your p is 1 over 10,000, even your n reaches 25,000, it is still less than 5, okay, so I will use Poisson distributed, but now here I do not know what is the lambda, because it depends on your n, therefore I let it be lambda first. Now, rewrite this probability. If it is at least 1 means it is 1, 2, 3 onwards. So since we do not know when to stop, so I will use the complementation rule, which is 1 minus the value which is before 1. Before 1, that is 0. So 1 minus probability of y equals to 0 equals to 0.963. So from here, again, since it is Poisson distributed, I will write 1 minus e negative lambda. Now remember, when it is 0, okay, x is Poisson lambda, px equals to x, it will be e minus lambda, lambda x over x factorial. So this will be 1. This is also 1, okay, when the x equals to 0. So then, now here I will only get e lambda, e to the power of negative lambda. Alright, so here I will write equals to 0.963. Then now, my e negative lambda is basically 1 minus 0.963, that is 0.037. And now to get the lambda value, since lambda is the power of the exponential, therefore to eliminate the exponential, we need another formula. Take ln both sides. Alright, so ln EA is basically A, because the A moved down, ln E, then this is A times 1. That is going to be A. So every time when we need to eliminate the E, just take ln both sides. So ln E minus lambda equals to ln 0.037. Then from here, minus lambda on the left hand side, ln 0.037 on right side. So now the minus move to the other side, then you will be getting 3.30. Okay, then now here, the question asking for n. Okay, we know that it's supposed to be not binomial distributed. So for binomial distribution, the mean, which is the lambda, equals to n times p. Okay, so now here we already found the lambda as 3.30. Therefore, your n is unknown. P remains at 1 over 10,000. Therefore, now your n is 3.30 times 10,000. Then that is going to be 33,000. Okay, so done for the D. Number 6. Alicia models the length of time in minutes by which her train is late on any day by the variable x with probability density function. Fx is this function where the x is from 0 to 20. So all these are in minutes. Otherwise means other x values, the function is 0, means undefined. Now A, find the probability that the train is more than 10 minutes late on each of 2 randomly chosen days. Okay, this is on any day, one day. Now, from here, before we consider 2 days first, right, we need to consider 1 day. What is the probability that it is greater than 10 or more than 10 minutes late? So more than 10 minutes late, since it is continuous random variable, right, which is the probability density where the probability density function is given. So we are finding this integration, this probability using integration. And now your x is from 0 to 20. So when more than 10, that means it's from 10 to 20. So now I need to integrate from 10 to 20 the function 3 over 8,000, then x minus 20 squared dx. Now we have a formula for integration. So integrate, you can use this ax plus b degree n dx. This is going to be ax plus b with degree of n plus 1 over n plus 1. Then you differentiate ax plus b, that is a. Okay, if with limits, then you add on limits, right? So if without, then you just plus c. Here, I will factorize 3 over 8,000 first. Okay, then you integrate this quadratic function using the given formula. And remember, the formula is valid when the n is not minus 1. Okay, that's the condition. Therefore, now I will integrate. So it becomes x minus 20 degree 3 over 3. And when differentiate x minus 20, that is 1. This is how I get the a here, because you differentiate ax plus b. And now with limits 10 to 20. So now, before I replace the values, the limits 20 and 10 into the function, I will cancel off the 3 first. So here I will only get 1 over 8,000. Then x minus 20 cube. When the x is 20, I will get 0 cube. Then minus, when the x is replaced by 10, I'll get negative 10 cube. Okay, then from here, you will be getting 1 over 8. Because 10 cube, negative 10 cube is basically negative 1,000. Then there is another negative outside. So 1,000 divided by 8,000, that is 1 over 8. But this 1 over 8 is for 1 day. And now it's mentioned that late on each of 2 days. So therefore, the probability, okay, and now we know that it will be independent, right? So it will be 1 over 8 for first day and another 1 over 8 for second day. Therefore, you are getting probability of 1 over 64. So this is for 2 days. B, find Ex. So Ex is defined as integrate x fx dx. And then the x from 10 to 20. And now here, when you look at this function, okay, this is your fx. This is your fx. Now, when x fx means I just need to times x to this and factorize this constant. So I will write equals to 3 over 8,000 integrate from 10 to 20 x times x minus 20 squared. So before we integrate, we need to expand the quadratic first. So it will be 3 over 8,000. Now for the quadratic expansion, you may just use this formula a plus b or a plus minus b, that is a squared plus minus 2ab plus b squared. That is the quadratic expansion. That means now here I will be getting x squared minus 40x plus 400. And do expansion first. 3 over 8,000. Integrate from 10 to 20. Just do expansion. So that is x cubed minus 40x squared plus 400x. Okay. And then now here, when we integrate, we always plus 1 degree to the x. That is this formula. Integrate x degree n dx. You will be getting x degree n plus 1 over n plus 1 followed by plus c. Okay, so x degree 3 becomes x degree 4 over 4. Then minus 40, x squared becomes x cubed over 3 Then the 400x becomes 400x squared over 2. Then now here you will get 3 over 8,000. Replace the x by 4. So 20 degree 4 over 4 minus 40 over 3 times 20 cubed. Then plus 400 over 2. This is basically 200. So 200x squared. Okay, then minus when the x is, oh sorry, you shouldn't integrate from 10 to 20 because your x is defined from 0 to 20. So I overlooked that. Okay, so the 10 is previous question. So all this should be from 0. So all my lower limits are wrong. So here's 0. Okay, then when you replace the x by 0, all these 3 terms will be 0. Then now here, I will get 5 for the final answer. So done for this question. Part C, the median of x is denoted by m. Show that m satisfies this equation, and hence find m equal to 3 significant figures. So now if this is median, that means because your x is from 0, okay? Your x is from 0 until 20. So that means from 0 until m, this is 0, this is 20. Since the m is median, median means middle value, the probability will be 0.5. So I'm going to use this concept. Therefore, px between 0 and m, it will be 0.5. Okay, so now integrate. The probability is just to integrate. So that means here it will be integrate fx dx from 0 to m. That will be 0.5. Okay, so the integration actually we have done just now, which is this part. Okay, this is the integration. So I will just copy this result and change the limits accordingly. Okay, so it will be 3 over 8,000, then copy this, rewrite everything except the limits. So here I will write 3 over 8,000. Then x minus 20 cubed over 3. Limits from 0 to m. That equals to 0.5. Then now the 3 will be cancelled off. Okay, and replace the x by m first, followed by 0. So here I will get 1 over 8,000. Then m minus 20 cubed minus 0 minus 20, so minus 20 cubed. That equals to 0.5. Okay, then now here times the whole equation by 8,000. So I will get m minus 20 cubed minus 20, you cube it, it will be minus 8,000. That equals to 0.5, equals to 8,000 times 0.5. Okay, therefore, I will be getting m minus 20 cubed. Now, 8,000 times 0.5, this is plus. So when you move the plus to the other side, it becomes minus. Therefore, it becomes minus 4,000. Okay, and now here, we need to prove this. Okay, so we already prove, or we have shown. Right, and now the next question is hence. Hence means use a previous expression, find m equal to 3 significant figures. So now to get the m, I will move the cube to the other side, means I take cube root. So now here, m minus 20 equals to cube root of negative 4,000. Then now, this minus 20 will move to the other side. So m equals to 20 plus cube roots of negative 4,000. And now just calculate this whole value correct to 3 significant figures. That is 4.31. That is your answer. Now state one way in which Aletheia's model may be unrealistic. Okay, so from here, look at the original question first. Okay, now Aletheia models the length of time in minutes for the train to be late, right? By which her train is late. So this is a function for a train to be late, right? So that means if unrealistic means that it does not consider whether the train is being early, or the time for the train to be late is greater than 20 minutes, because she is just testing up to 20 minutes, right? So that will be the solution for part D. Okay, so one way may be unrealistic. So you say Aletheia's model does not allow for trains more than 20 minutes late. Okay, or probably you can just write or does not allow for trains being early, because she is just testing on the trains late for up to 20 minutes. Okay, so that will be the solution for part D. Now we have come to the end of the video. Thanks for watching. Please subscribe to the channel and also share this channel with your friends if you enjoy watching my video, and also stay tuned for more upcoming videos. Thank you everyone. Bye.